Panned a lot to the right. My name is Jaidev, and I am a data scientist at Cube26 Software Private Limited. I started off as a QA engineer. I used to work in data science before that as well, but it's over, the first few years of my career I spent as a build and test engineer. And this talk is about how, what I think data scientists could learn from CI people and their habits and their culture. So yeah, that's redundant right now. So recently, Peter Norvig was asked in a Q&A what he thinks about the place of software developers in machine learning research. And that is his answer. It is important for machine learning experts and software engineers to come together to develop the best practices for the development of ML libraries and systems. We need new testing processes that involve running experiments and analyzing results. And that this is a great area for software developers and machine learning enthusiasts to come and work together. The interesting thing here is that Norvig is talking about testing not as quality control, but testing as a way of evaluating machine learning models. So this is broadly what I'm going to talk about today. When I say continuous integration, I don't literally mean just continuous integration, like I said. It's something like a placeholder term for sysadmins, DevOps, QA people, and the systems and their habits and their cultures, all that which comes with it. So I'll start with an example, and at the end of the talk, I'll come back to tell you about how this project evolved. At Cube26, we recently released a suite of apps called the Rios suite of apps. And one of them is a messaging app called Rios Message. It classifies your SMS into three categories. One is personal, transactional, or notifications, and spam. So to build and deploy the classifier, all we had initially was a massive Python script with a single input, which was just a CSV file. And that file was a dump from a table that was in Postgres. We had some pandas functions written down to clean these messages from that CSV file. We would run some simple functions to remove Unicode, emojis, whatever we thought was not relevant to categorizing a message into these three categories. So we also didn't have any labels. It wasn't labeled data, supervised. So we used a set of regular expressions to label a subset of the data. And on this subset, the model was trained. So we used to send the model results to everyone in office, and they would sort of go through it quickly and give a brief qualitative idea of how badly they thought the model was doing. When we were somewhat satisfied with the results, we would dump the model coefficients into JSON. That JSON would then go to the Android developers, and they would use that configuration to implement the same model on their side. So it's easy to see how this could not have scaled. It's not modular at all. It was, like I said, one massive Python script, which simply took one command line argument, which was a CSV file. It was also very redundant in places, and it was, as we added more data and more functionality, so it was getting increasingly difficult to debug. So I'll come back at the end of the talk to this example to see how we fix this. So this here is a broadly representative, very general sort of a data processing pipeline. That box that you see here is called the ETL part of the pipeline. ETL stands for extract, transform, and load. You start with a source data store, and you end up with a sink data store. These data stores don't really have to be literally data stores. They could be anything. A source of data and a sink of data, that's all. So the ETL part of the process is the most data intensive one. And by that, I don't mean that the other parts are not data intensive. It is just that it is within this box that you have to treat your data for what it really is. It is really raw data. As soon as your data has left the box, it's no longer raw data. It is features, it can be statistics, it can be model coefficients, whatever. So it is in this box that your developer side has to show off a little bit, and it is outside this box that your data scientist comes into the picture. If you'll excuse me for just one moment, I seem to be getting notifications. I should turn this off. Oops. Yeah. Sorry about that. So after you have extracted, transformed, and loaded your data, you do some validation, which might allow you to select a better model. Then you might deploy that model on a particular platform, and that model might be writing predictions to either a web front end or a database or whatever it is. Now these steps, training, validation, and model selection, they are not necessarily well separated in time. You could be cross-validating one model while you're already training another model, and a third one might actually be in production. So the thing is that we tend to think about a pipeline as something sequential, one thing after the other. We are not accustomed to thinking about it as something that is asynchronous. So you can't really think of this as a pipeline, which is difficult because this is what you would write if you were actually writing a Python script. So how do you bend the spoon? You think that there is no spoon. Think that there is no such pipeline. These are all actually microservices. These are independent systems that only happen to be loosely coupled. So I'll be talking about a few ways of how we can get that done. So this is a word cloud of the text of all the proposals made to PyCon. And now humor me a bit over here. As a species, I think we are spending an unreasonable amount of time and money simply beating data into shape. That's almost all. That's what almost all our conferences are about nowadays. Although I can't really justify this, but I think that this is overkill. Dealing with data ought to be simpler. It ought to be easier than the way we're doing it these days. And I've met people who very sincerely believe that if they can get a lot of data accumulated in one place, it will automatically start becoming sentient. And this is for probably no fault of their own. It's clearly ridiculous. Data may not be sentient, but there are certainly some advantages to thinking of data as a living entity. In that, think about it as something that needs to be grown, something that needs to be cultivated before finally it is harvested. So instead of data mining, let's start thinking in terms of data farming, and here are a few ways of doing that. Abstract away almost everything that has to do with the ETL framework. We as a community, the data science community, haven't paid much attention to it. Machine learning systems have grown super sophisticated over the past few years, but data management systems, the same systems on which these machine learning systems are dependent, have lagged a little bit behind. So let's stop thinking of raw data as an inanimate entity, that you only have to dig through before you can get to the gold. The digging itself is part of your software, and therefore is subject to pretty much the same dangers as any other kind of software development. So build abstraction layers, services, and all kinds of tooling that you would do around any other microservices. So do those same things with your ETL pipelines. Now, this might sound very obvious, but you'd be surprised at how infrequently we practice this. For example, almost all development that data scientists do is based off local flat files, and it happens within the IPython notebook and things like that. The excuse is that we are just building prototypes, and it's not really our job to go ahead and deploy these prototypes. We don't really know about larger systems, more integrated systems. But we know how fast the boundaries between data science and all other types of development are shrinking. So in that light, we have to learn to work with larger, more integrated data sources. Even if you're just building a prototype, it's still not very healthy to simply restrict yourself to that prototyping thought process, because you don't know how long the prototyping is going to take, and you don't know how many more intermediate systems or scripts or functions, files, whatever data you might end up producing in the meantime. So at least as a favor to the people who are deploying your work on larger systems, learn to use integrated systems. Even if you're using something like the Iris dataset or something like that, try to use SQLite instead of CSV. The cloud is your friend, so the sooner you are comfortable with remote or cloud-based storage, distributed storages, the faster you can deploy your apps. And here are a few libraries that can help you do that. So Sputnik is a library that manages data packages. You take a directory with your data in it, you add a JSON which describes the directory and the metadata for whatever you have in the directory. And Sputnik will make a tarball out of it, allowing you to deal with the whole thing as in a much more atomic fashion than otherwise. Datrient is another data management library that leverages the local file system itself. So it's very common to have a very messy laptop with files all over the place. But Datrient will exploit this mess to provide some sort of discoverability into your data. So Mac users can think of Datrient like as a spotlight for data sets, which is operating locally. So you can also think about it as a trade-off between the rigidity of your data hierarchy and the flexibility that it provides that any heterogeneous data storage can provide. Then there is Conduit, which is used for managing data for HPC simulations. And it's a hierarchical data storage system, so it represents your data as a graph. And this graph can seamlessly integrate with the in-memory data and the serialized data that is on your disk or it's there in your program. Finally, there is PySemantic by yours truly, which automates all the pandas code that you might write for cleaning and validating your data set. So that was all about data ingest. Now let's talk about automating machine learning. It's a very widely studied problem, and one of its most popular forms is the AutoML project. It's also known as the CASH problem. CASH stands for Combined Algorithm Selection and Hyperparameter Optimization. The motivation for studying automation of machine learning is simple. There's no single model that will work well on all data sets, not even neural networks. So, and of course, most machine learning algorithms are highly sensitive to the choice of hyperparameters. So there is this flowchart. I'm not sure. Is it properly visible at the end? No. Okay. Right. Okay. This is just weird. I think I'm just going to open this in a new tab and then magnify that. Right. Okay. Yeah. So is it visible now? So these xtrain, ytrain, xtrain variables are as usual. L is the loss, and the interesting thing here is this parameter B. It denotes your budget. That could be your time or your processing power or anything like that. Then this ML framework box is also as usual. There's a preprocessor, there's a feature extractor which ultimately feeds into a classifier. The Bayesian optimizer block on top there is a process that fits a model between hyperparameters and performance. So actually take a moment to think about that. You want to automate the training of a model, and for that you're fitting a model which, given another model and parameters, predicts the performance. All right. So there's also this meta learning block, which learns the performance based pretty much on the same input, except this time the input is restricted to your data itself. So it's so given a data set, it will predict the performance. You know, like a domain expert. So when we say things like decision trees are more likely to perform well for categorical variables, that's the kind of thing that this meta learning block is trying to fit. Finally, we build so we build an ensemble from all the models that we generated or a subset of them. And whatever models have been performing well, we just try to, this is the block that will build an ensemble out of it. Thankfully, there is also a convenient implementation of this, which is called auto-sklearn. Actually, this is what Andreas Mueller spoke about in his talk at SciPy this year. And he said that if machine learning is so ubiquitous, one should just be able to use it without understanding libraries. So automate machine learning and simply just use it. That was the broad point. Am I right? Yeah. So now if you think about it, that is exactly how sysadmins think. They don't want to be bothered with understanding the details of your application. They would much rather find something that works well and use it for as long as they can. And now actually allow me to digress a bit. About 2 years ago, I used to work on the nthought Python distribution, or Canopy as it is called now. I was briefly a part of the build system team that was responsible for making Python packages that would work across different architectures and platforms. Now, the one rule of thumb that the build system team had was that upstream is always broken. If you build a Python package from the source code as is, it's very likely to fail on one or more platforms. I mean, there were very, very few packages which worked just as you got them from GitHub. So we used to write our own patches to fix these broken packages. And we had patches for almost every project which we would apply before building the package and then shipping it out to our customers. Scikit-learn is a precious, it's one of the precious few packages that didn't require a patch. So it's a wonderful library that you should study. Like requests, it's one of those modules that are an example of what good Python development should be like. So it's very natural that scikit-learn follows the Zen of Python. A scikit-learn developer would say that explicit is better than implicit. But then a sysadmin would ask, is it really explicit? Is it really better than implicit? For sysadmins, things need to be so automated that making them reasonably explicit is almost impossible. In fact, they are even reluctant to update packages very frequently, lest it might break something else. So it's actually one of the reasons why most enterprise Linux distributions have outdated packages. They just care, like I said, they just care about building and running stuff, which is another reason why projects like AutoML are important. They allow you to run a lot of models fairly easily and in a hands-off, more or less automated manner. But then with great power comes great responsibility. Automating machine learning is very expensive. So we need to formalize the search space mindfully, the space over which you're searching for hyperparameters or your models or whatever it is. You need to formalize that space mindfully. Think about which parameters are continuous or which parameters are discrete. Especially in sklearn, there are combinations of hyperparameters that are not compatible with themselves. There might be a regularization method which is not supported for a particular class weight parameter or some other parameter for any given classification algorithm, for example. So when you are iterating through a grid that you're searching, the grid search reaches an incompatible set of hyperparameters and it fails. So unless you've been logging everything up to that point, you have to start all over again. So, and normally the habit is to sort of stuff everything you can find into the grid and then just run it as fast as you can and for however long that you can. But you can restrict much of the grid even before you start if you actually think it through properly. And there's also randomized search, which is basically tries to, it's pretty much like that Bayesian optimizer block that we saw earlier. So out of the three things here, the choice of estimators and hyperparameter selection can be done by grid search and auto-sklearn. But unfortunately, there is no straightforward strategy to automate feature extraction. In fact, I would say neural networks is the only thing that I can think of which can, to some degree, let you do feature extraction in an unsupervised manner, which is showing reasonable prowess in real problems. But even in general, I mean, feature extraction pre-processing is something that has to be done by hand a few times before you can reach a reasonable choice. Now, this is a sample of how you can do all of that in Luigi. Luigi is an open source pipelining framework which is built by Spotify. Think of it as a distributed build system like Make, except that it is distributed and it's a lot more flexible. It's all Pythonic. You can write all your code in Python. And you can define tasks within the pipeline. Sorry, I think I need to magnify this as well. Yeah, it doesn't seem to be doing a lot better. Anyway. So Luigi tasks can be parameterized, just like Jenkins builds are parameterized. And they can be parameterized by any Python object as long as it is hashable, of course. So you can use the estimator itself as a parameter. You can run a cross-validation loop for a given task. And you can, at every iteration of the loop, you can send its output so that you can see it on a dashboard or something. You can visualize real time how well your model is doing. For the grid search, you can just keep producing the best estimator for every result, and you can keep storing it as build artifacts, which you can then just automatically hook it up into your model. Right. So that was all about hacking and creating models. Now let's talk about inference and quality of the models. There was another interesting talk at SciPy this year by Katie Malone about using tools from psychometrics for data quality evaluation. Data quality is again also something that we are not very accustomed to think about. We tend to be so preoccupied with model performance that we don't think of data quality as any sort of a measurable, quantifiable entity. Do look up the talk itself. It's pretty extensive, but I'll provide a little bit of a summary here. The talk says that predictive modeling is not simply the same as simply building a model. It needs to be a lot more comprehensive than that. It needs to be something with insight. So iterating over different models shouldn't be limited to simply changing your feature extraction and pre-processing or hyperparameter selection. You need to go all the way back to your original data. This ties into what I said earlier about data farming. You need to have the same intuition for your data as you have for your model. So specifically, that means asking questions like what data set would yield a good performance for a fixed model. So essentially turn around the intuition for building a model. You'll quite likely find that simpler models perform much better on good data sets, and complex models won't do well even if your data isn't good enough. And there's of course the added overhead of building and maintaining complex models, which you want to avoid anyway. Right. Speaking of inference and insights, there was another interesting talk at SciPy by Bhargava Subramaniam. Is he here by any chance? Okay. Actually, he was going to speak about somewhat related topic, but I think for some reason he had to cancel. Anyway, so he points out that performance metrics are not as important as model insights. In fact, most people don't even understand what precision and recall is. So the inference has to focus on insights about your data. Now, as an example, I was trying to build a model that fits the talk selection process that happens here at PyCon. And the model was doing fairly well, but instead of pushing for an extra percentage in the accuracy, I realized that it's much better if I spend time simply visualizing the decision tree and to see how well that tree reflects our talk selection process, rather than simply being a prediction model which tells you whether your talk is likely to be selected or not. So I by the way, might do a lightning talk later about that. And in that spirit, the software you build ought to be modular with respect to, first of all, the original data, then the interpretation of the model, and then finally the metrics, just as a formality. Don't let the metrics take undue precedence over the data or the learning process itself. Oops, I skipped a slide. Yep. Oh, yeah. So these are a few things that you could that could help you with the visualization beyond Matplotlib. Bokeh is wonderful for dynamic plotting. You don't have to know HTML or JavaScript. It runs as a server. You can just keep sending it data to have it plotted dynamically. Instant dashboards, that's how I think of Bokeh. Chaco is another library that provides a lot more interactivity than Matplotlib, but it's somewhat difficult to hack, not very easy to get it up and running in a browser. There are many other libraries like Seaborn or GeoPandas or NetworkX, which will provide domain-specific data visualization. And I urge you all to just use these domain-specific libraries instead of, try to resist the temptation to write them on your own. Finally, we come to the deployment part of it. Now, the easiest way to deploy models is to use simple serialization methods like pickle or JSON. The joblib from sklearn will do fine. And then writing wrappers around that same pickled or serialized model on the client side, especially if it is not a Python client. sklearn compile trees is a project that compiles tree-based or ensemble models from scikit-learn into object code, which your client can then read from. Now, you could port almost any machine learning algorithm to any platform, but if it is a linear model, then the advantage you have is that the client is simply trying to evaluate a dot product. So, evaluate linear models first, and if you think you can't work with them, make absolutely sure that you can't work with them. And only then move on to more complex implementations like kernel methods and so on. So an interesting deployment solution that has emerged recently is the serverless paradigm. Alex Casalboni is a developer at Cloud Academy, where they are pioneering the serverless paradigm, especially in the scikit-learn and Python space. He says that very rightly so, that the data science community is stuck at the level of designing ad hoc models, which are mostly just prototypes with very thin layers of customization built around them, which cannot be embedded or extended by other developers. So the serverless paradigm is one of the ways in which you can make your prototypes production ready with little or no effort. Now, even if you want to keep things simple with serialization, it takes a lot of effort to scale it to make it distributed. You will also have to put a lot of thought into how you want to expose the API, how you're going to authenticate it, and how you're going to update it. So one of the easiest things you could do is simply write a Flask or a Django wrapper around it. But even that doesn't provide enough elasticity, and scaling is still non-trivial. So there are things like AWS Lambda. It's a service that allows you to just deploy scripts onto AWS. It takes care of the scaling automatically. A combination of this and the Amazon API gateway is pretty much all you need for deploying and scaling your scikit-learn code. That's what, Alex has done a bunch of demos around that. There's also a lot of things you can play around with on the Cloud Academy website. So do give it a shot before you try to deploy a model in complicated manners, much more complicated than this, that is. But unsurprisingly, it's AWS Lambda and API gateways are slightly more on the expensive side. So to recap, if there were a few key points that I would like you to take away, the number one would be to abstract away your ETL code. Second, and perhaps more important, is that searching for a good machine learning algorithm, tuning its parameters, should be done in a much more thoughtful manner than just brute force. And finally, insights are more important than metrics. If you can't explain your model, you probably need to reevaluate it. And of course, all of these are systems that ought to be modular, use microservices wherever possible, use packages, independent libraries wherever possible. So coming back to the example from the beginning, our Postgres database was being populated by Kafka consumers, which in turn were reading data from all the devices on which our app was running. So instead of taking the dumps from Postgres, which itself was being populated by the Kafka consumers, we set up a streaming application in Spark that directly connected to the Kafka consumers. And we sort of modularized it as an entire data ingest system in itself. Spark itself has great data cleaning functionality, so we could manage to get the streaming application to absorb even the pre-processing layer which we earlier had. The data then goes to a set of Luigi tasks which are running parallelly to produce newer and newer benchmarks on the classification problems, and ultimately they export the model configuration, which then gets deployed on the apps. And all of this is triggered by Jenkins. Primarily builds are triggered by cron jobs and whenever commits are made to the staging branches in Git. Oh, so it seems that we will probably get some time for a Q&A. So thanks for your time. Thank you very much. Do we have any questions?
So in your pipeline, there was a custom part at the end where I think you used custom JSON, right? You have your own format to store the coefficients.
Yeah.
And so I think one place where the current system is quite lacking is in trying to serialize models and communicate them to the developers, or to the your live system. Yeah,
we actually fixed that as well. Now it's a shared library that simply goes to Android and they can just use it as a system library.
Okay, so you're not using a JSON anymore?
No, we are not using a JSON anymore.
But
because that was also something of a security risk for us.
Okay, so that's for linear models, right?
Yeah.
Have you published that?
Sorry?
Is that open source?
No.
No.
I could tell you a few things, but can't go into too much details.
Jaidev? Hello?
Yeah, I can't see you.
Here, I'm standing up.
Oh, hello. Hi.
Could you show the previous slide, the one for this? So I just wanted some clarification. You are not doing a dump, right? You're not doing the dump.
There's no dump.
Okay. Instead, you're using Kafka to stream.
Yes. It's all in memory, and the only dump happens at the end where there is still JSON serialization, but that's for ourselves at the backend. Android isn't using that same dump.
My question is actually not about the machine learning aspect. I was interested in the Kafka aspect.
Right.
How well was Kafka working for you for this?
We're pretty happy with it.
Okay. You have any benchmarks that you will be talking about later or something?
I don't know about any benchmarks, but I could get them for you.
Okay, thanks.
Yeah. I mean, if for what it's worth, we have a few 100,000 apps or users sending us data, and our Kafka consumers, they're running on AWS. I'm not sure exactly what the configuration of that is, but it's for a few 100,000 customers that have been sending us events every few hours a day per user. It's been working fine for the last 6 months, and never really had too many problems with that.
It's probably like 10 million requests at a time or something like that?
No, nothing of that scale.
Not like that?
No.
Okay.
Hi, here. So you said the simple models with better quality of data works well rather than complex models with not so good quality of data.
Yeah.
But most of the times that quality of data is not in our hand. I mean, whatever data is with client, we will use that only.
Yes.
So how do you define that better quality of data, and I couldn't understand.
There is no easy answer to that. And what I meant was, if you can find better quality data, which is probably a subset of your original data, or you could probably handcraft some features to make it better quality or drop some garbage from that data, then that's what I mean by better quality data.
Okay.
Yeah.
Hi.
It's not an automated or a programmatic answer to what is better quality of data. which is again what I meant, that we are not accustomed to thinking about it. So we should probably try to formalize it a little. What does it mean when we say quality of data? I think there's a gentleman here who needs.
Hi.
Yeah.
So did you actually evaluate, did you also had a chance of evaluating Luigi versus Airflow for data pipelines?
Sorry?
Did you evaluate like Luigi versus Airflow ever for pipelines?
No, I am sorry, I don't
I'm
follow.
just
Luigi
curious,
with what?
Luigi with Airflow.
Airflow?
Yeah.
No, sorry.
Okay.
So have you used Airflow?
Yeah, actually used it. Like the one problem I faced with Luigi is like, when, if I had like heavy tasks, like 3 million tasks,
3 million tasks.
I mean, like in a data pipeline, like when I
Yeah.
sharded extensively, like Luigi wasn't really giving a good performance, but Airflow was promising that technically they are like infinitely scalable. I mean, like, so I just
Not exactly. I mean, Luigi does have its constraints, and they themselves make it explicitly clear that you probably shouldn't use Luigi as a streaming in a streaming application. It's meant for batch processing. So if you're spawning maybe 1 million tasks, that you might want to think about it again. Why would you want to spawn 1 million tasks instead of putting those million pieces of data into a single task and then having multiple or a much less number of tasks?
yeah, that worked.
Ideally,
perfectly.
I've found that having you should spawn only as many tasks as you have cores. That works wonderfully well. Yeah. Okay, so thanks a lot. Thank you very much.